Hello students, welcome back. We'll move on to the next topic, that is trusses. So what is a truss? A truss is a structural member made of number of bars joined together by pin joints. So till now we have studied about bars. So truss is nothing but a structural member made up of joining such different bars. So several bars are joined together with the help of a pin joints. So such a thing is called as a truss. You would have all seen the trusses in fabrication of roofs or in the bridges and all. By definition of elementary strength of material, bar can carry only axial load. So this we know that bar can carry only axial loads and deform axially. All the bar segments of truss are subjected to only axial loads and no transverse shear loads or bending moments are experienced by any segment of truss. So this is the condition for the truss. So since the truss or bar carries only axial loads, so it applies same even for the truss. So in the trusses, it carries only axial loads and no bending loads or shear loads are acted on the trusses. The segments in the truss structure can be modeled using the bar finite element. These elements are called truss elements. For example, this is a truss element. It is given like this. So these are the different bars. You can see this is a bar, 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 this is a bar. And all the different bars are joined with the help of a pin joints. So that pin joints will consider it as nodes. And the bars will consider it as elements. Okay. So here we have 1, 2, 3, 4, 5 nodes. And elements 1, 2, 3, 4, 5, 6, 7 elements. And unlike in the bars it was in one dimensional one. So the displacement was only in the one direction, that is Q1. Whereas truss is a two-dimensional one, so the displacement will be at each node, it will have 2 degrees of freedom. So displacement will be in Q1 and Q2. Okay. Similarly, at 2, it will have Q3, Q4, continuation, Q1, Q2, Q3, Q4, Q5, Q6, one in the x direction, one in the y direction displacement, Q7, Q8, Q9, Q10. Okay, so such will be the displacement, and the perfect truss should follow this equation, that is m is equals to 2j minus 3. Where m is equals to number of element members, j is the number of joints. For example, if you take this truss member, what is m number of element members? How many elements are there? 1, 2, 3, 4, 5, 6, 7. So m is equals to 7. J number of joints. So how many joints are there here? 1, 2, 3, 4, 5 joints. So 2j minus 3. So 2 into 5, 10. Minus 3 is 7. So 7 equals 7. So if it satisfies this equation, it is called as a perfect truss. Okay, it should satisfy this equation. Next, assumptions. In exam, he might ask you this assumption. It is quite important. Assumptions of the trusses. So here in the truss member, while solving, we assume few things. First one, the joints of the truss are assumed to be frictionless pin joints. That is, all these joints of a truss member are assumed to be frictionless. Of course, there will be some friction in the pin joint, but we are assuming it as a frictionless pin joint. It is very negligible. Next, forces are applied only on joints. Thus, truss structure consists only of 2 force members. Every truss member is in direct tension or compression. So here in a truss member, the forces should act only at the nodes. That is, this point or this point, this point, this point, this point. The forces should not act on the element. Okay, the forces cannot act on the element. That will be wrong. Okay, so when the forces are acts on at these nodal points, the elements will be subjected to direct tension or compression. No other loads, no bending or no shear loads. Okay. The self weight of each bar of a truss is neglected in comparison to external load applied. So the self weight of the truss member will be neglected while analyzing the truss member. Okay. So that is about the truss member. Next we will move on to the derivation. So element derivation, that is element stiffness matrix derivation of a truss member. Next, derivation of element stiffness matrix of a truss member. So let us consider a truss member in the global coordinates. This is in the x and the y coordinate. So let us consider a truss member here, that is 1 and 2 of element 1 at some angle, that is at an angle of theta. Okay, let me coordinate it. Let me write the coordinates. So node 1 is in x1, y1, and node 2 is x2, y2. Okay, and the displacement at each node, since it's a two-dimensional, displacement at node 1 is q1 and q2 in the global coordinate system, that is with respect to x and y, and displacement at node 2 is q3 and q4 in the global coordinate system. Okay, so here, apart from the global coordinate system, there will be a displacement even in the local coordinate system. So in the local coordinate system, that is, what is local coordinate system? In its that passes through the element. So here the local coordinate system is this zeta axis. So here in the zeta axis, the displacement or the displacement will be at node 1 is q1, at node 2 is q2, that is in the zeta axis itself, that is in the local coordinate axis itself. Okay, so here we'll move on to this next figure. So you can analyze this figure how I have written here. So this is in the x and the y. So when this truss element, so let us assume this as some displacement. So this is a truss element. You can see here the same truss element I have written here. This is 1 and 2. The same thing I have copied from here, 1 and 2. Assume it has, due to the application of some load, there is some appreciable movement in the truss element, or there is an appreciable deformation in the truss element. Okay, so it has moved from this position to this position. It's just an assumption, practically doesn't move so much. So just for the derivation purpose, we are assuming the movement like this. So when it moves like this, what and all it has moved in the global coordinate, it has moved q1 and q2. Similarly, at this point, it has moved q3 and q4. Okay. Next, in the local coordinate, it has moved small q1 and small q2. But in order to represent the small q1, how will you write? So just write the dotted lines here from 1 to this next 1 point. So even this is 1 here. So till this point, write the dotted lines. This is the q1 distance. From here, drop the dotted lines to this point on the element, on the first element. Similarly, from here, drop the dotted lines to this point. Okay. So now you got a triangle here, just for your ease and for your understanding. So the distance between this point and this point, let me take this as AB, this as small a, and from here to here is small b. And q1 is nothing but small a plus small b. Similarly, you've got one triangle here, and you have got one more triangle at this point. So here you can see it is at an angle of theta, and this is 90 degree, and even this is 90 degree, and this is theta. Similarly, here it has moved through a distance of q3, the dotted line, it is at an angle of theta, this is 90 degree, and even this is one more triangle, this is 90 degree, this is theta. So from here to here it is C, and here to here it is B. This dotted line, drop it here, and from here this one more dotted line and drop it here, you'll get C and B. So Q2 is nothing but C plus D. Okay. So any doubt on this, you can, you're free to ask me or call me at any time. So figure truss element in global coordinate system. The element of the truss are in various orientation, and thus two coordinate systems are defined. First is local coordinate system zeta and global coordinate system xy. That's why I said since it's in various orientation, we have two coordinates. One is xy, that is global coordinates. Other one is zeta, that is local coordinate. Okay. Let theta be the angle made by local zeta axis with positive x-axis. So local zeta axis and the positive x-axis angle is theta. This is the angle made. The global coordinate system xy is fixed of course xy is fixed and does not depend on the orientation of the element. In global coordinate system, every node has 2 degrees of freedom in 2D space. That's what I said. Every node has 2 degrees of freedom, that is q1 and q2 here, that is the displacements. So therefore, displacement vector in global coordinate system is q is equals to, at node 1 q1 q2, at node 2 q2 q3, q3 q4 transpose. Similarly, element displacement vector in local coordinate system is small q. In the local coordinate, what you have? Just small q1 and small q2. Only this one. Small q1 and small q2. So q1 and q2. Displacement of node 1 in local coordinate system. So displacement at node 1, that is how far this node 1 has displaced in the local coordinate. In the local coordinate, it is displaced like this, in this direction, to this length, correct? So q1 is nothing but a plus b. Similarly, q2 is nothing but c plus d. Okay, q1 is nothing but a plus b. Next, from triangle ABC, from triangle AB and C, from triangle ABC, cos theta is equals to adjacent by hypotenuse. So cos theta is equals to adjacent by, this is 90 degrees, so this will be hypotenuse. So a by q1, you can see here, able to see. So this is a by q1. So a is equals to q1 cos theta. Similarly, from triangle DCE, from triangle DCE, sin theta is equals to opposite by hypotenuse. So what is opposite? This one, D. D is nothing but B. Opposite by hypotenuse. This is 90 degree. So hypotenuse is q2. Okay. So B by q2. Therefore B is equals to q2 sin theta. Substitute equation A, which is equation A. This is equation A. Substitute in these two in equation A. We've got A and B. So q1 cos theta is A. q2 sin theta is B. q1 is equals to q1 L plus q2 M. Cos theta and sin theta, I am taking it as L and M. I am taking it as L and M, that is cos theta and sin theta, which is nothing but the direction cosine. So I have got q1, that is small q1. Similarly, q2 I can directly write it as q3 cos theta plus q4 sin theta, which is nothing but q2 is equals to q3L plus q4M. Now, representing equations B and C in matrix form. That is, if I write this B equation and C equation in matrix form, I have q1 q2 is equals to, you can see LHS, q1 q2 is equals to, q1 q2 is equals to LM, write the coefficients here, LM, first is LM 0 0 0 0 LM. Next what I have, q1 q2, q1 q2, next I have q3 q4, q3 q4. So if I multiply this and this, I'll get the same equation. So this I can write it in a much simpler form. Small q is equals to, this is matrix T or transformation matrix T into Q, where T is the transformation matrix. Where to calculate direction cosines, that is L and M, we have, if you take an element LE, the first one, and this is the first node and the second node, and it is at an angle of theta. Coordinates is x1 y1 and x2 y2. So what will be this length? This length is nothing but x2 minus x1. This length is nothing but y2 minus y1. Am I right? So you can see here the coordinates of this is x1 y1. So what will be this length? x2 minus x1 will be this length. Similarly, y2 minus y1 will be this length. Got it? That's what I have written, x2 minus x1 and y2 minus y1. So L is equals to cos theta, that is direction cosine. L is equals to cos theta, that is equals to, what is cos theta? Adjacent by hypotenuse. So x2 minus x1 divided by LE. M is equals to sin theta, that is opposite by hypotenuse. So y2 minus y1 divided by LE, where LE is equals to effective length of element. So next, from this triangle, what is LE? Square of the hypotenuse is equals to sum of the squares of the other two sides. So LE square is equals to x2 minus x1 whole square plus y2 minus y1 whole square. So LE equals to root of x2 minus x1 whole square plus y2 minus y1 whole square. So this is how you got the length of the element LE. Next, the truss element is a 1D two-noded bar element when viewed in local coordinate system. So we know the truss is nothing but an 1D 2-noded bar element when viewed in the local coordinate system. So strain energy equation of an element in local coordinate is, so we have the strain energy equation for bar in the local coordinate. We have the standard equation UE is equals to half Q transpose, small q transpose K dash. This is for an element. Remember, this is for element and small q. Substitute Q is equals to capital T into Q from equation 1. See, from equation we have got small q is equals to T into Q. So substitute Q is equals to T into Q. Q is equals to T into Q. So Q is equals to T into Q. So T transpose into Q transpose. K as it is. You can see here K as it is. Next for this you substitute T into Q. Okay. The strain energy in global coordinate. See here in the local coordinate. So now here in the global coordinate can be written as U is equals to half into, same thing, instead of small q you have to write capital Q because it is for the global coordinate. So capital Q transpose K into capital Q. Okay. It's comparing this and this equation. What is the similarity? K is nothing but K is nothing but T transpose. Here K is nothing. You can see Q transpose is this one, and small capital Q is this one. So whatever is left out, K is nothing but K transpose, T transpose, and T. Am I right? So K is nothing but T transpose, K dash, and T, which is the element matrix in global coordinate system. Okay, where K dash is equals to AE by LE 1 minus 1 minus 1 1 is the element stiffness matrix in local coordinate system. We know K dash, that is element stiffness matrix for a bar. So K is equals to, we have this equation T transpose K dash T. So what is K? So T transpose T is this one, transformation matrix LM 0 0 0 0 LM, right? The transpose of it. So transpose of it is LM 0 0 0 0 LM. Next AE by LE, K dash is AE by LE 1 minus 1 minus 1 1. Next T is LM 0 0 0 0 LM. Now multiply this and this, AE by LE common, multiply this first row and first column. So L into 1 is L. So you can see here this is, you get 2 cross 2, so you can multiply, and the final matrix will be 4 cross 2. So L into L is L, 0 into minus 1 is 0. Next is L into minus 1 is minus L, 0 into 1 is 0. So like that you have to keep multiplying L minus L minus M minus M minus L, L minus L, M. So start from multiply everything. M into 1 is M, 0 into this is 0. M into minus M is minus M, 0 into this is 0. Similarly this one. If you multiply everything, you will get this. And this matrix as it is in the previous step. This matrix as it is in the previous step. Okay. Next you multiply this and this. Okay. So K is equals to AE by LE. L into L is L square. Minus L into 0 is 0. Next L into M is LM. Minus L into 0 is 0. Next L into 0 is 0. Minus L into L is minus L square. L into 0 is 0. Minus L into M is minus LM. Similarly you multiply everything, all the things. Okay. So we'll get L square LM minus L square minus LM. LM M square minus LM minus M square. So how to remember this for the numericals? So very simple. It's a symmetric matrix. Okay. So in the principal diagonal elements, write L square M square L square M square. Okay. And I said it's a symmetric matrix. So this is minus L square minus LM minus LM M square. If you have L square M square, LM and LM common. Symmetrics. This side L square LM, 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 M square, M square. Okay. And wherever it is left out, write LM and LM. Very simple to remember. This is the stiffness matrix equation for a truss element. Okay. Next, equation 4 is element stiffness matrix for a truss element. That's all is the derivation. Further, in order to find the strain, you can continue with the derivation. Strain matrix for a truss element in local coordinate is equivalent to 200 bar element, which is given by epsilon equals B into Q. So epsilon equals 1 by LE minus 1 T into Q, where B is equals to 1 by LE minus 1. That is strain displacement matrix. Okay. So T into Q. Substitute T, substitute Q, Q1, Q2, Q3, Q4, since it has 2 nodes and 4 degrees. Each node 2 degrees of freedom. If you multiply that, you will get minus L, minus M, L, M, Q1, Q2, Q3, Q4. Just multiply this, this, and this. Okay. This and this. Minus 1 into LS minus L, 1 into 0 is 0, minus 1 into MS minus M, 1 into 0 is 0, minus 1 into 0 is 0, 1 into LS, L, minus 1 into 0 is 0, 1 into MS, M. Got it? That's how you derive the equation for the stream. So next, we'll move on to numericals on trusses. The numerical problems. First one. So it's a truss element given like this as shown in the figure. The distance between this fixed and this fixed point is 1 meter, and the distance between this and this is 1 meter itself. And a load of 100 kilonewton is applied on it, and this is the x direction and this is the y direction. So given values, E is equals to 210 GPa, that is 210 into 10 power 3 MPa, that is 210 into 10 power 9 Newton per meter square. We'll try to solve this in the meter, in keeping all the values in meter itself. Next, A is equals to 0.01 meter square. Determine the nodal displacement and stress in each member for the truss loaded as shown. Okay, so write the finite element model from this. Write the similar line diagram with this and this fixed. Start numbering first. This is a very important step. If you understand this step, rest everything is very easy. Start naming. So this is 1, node 2 and node 3. Write the coordinates of each node. Always the origin must be left bottom corner in the truss. I repeat, the origin should always be left bottom corner unless and until they have specified the origin. Okay, in the question. So here in the question the origin is not specified, so we will take as left bottom corner. You can take even other points as origin, but see, if you take this as the origin, when you write the coordinate for this, it will be in the negative. Okay, you don't want to deal with negative numbers and make it a bit more complicated. So if you take the left bottom corner as an origin, everything will come in the positive and it is easy to solve. Okay, so 1, I'm taking it as origin, so 0, 0. Next to 2, this is 2. What is the length? Distal coordinate, this is 1 and this is 1, because this is 1 and this is 1. So 2 is 1, 1. Similarly 3, this is 3. In the x direction 0, in the y direction 1. So 0, 1. Okay. Write the forces. So forces and the displacement at each node. In the bars we had only displacement in the one direction, whereas here we have displacement in the two directions. So Q1, Q2, Q3, Q4, Q5, Q6. Similarly, forces F1, F2, F3, F4, F5 and F6. So write the displacements. So this node is fixed. So Q1 will be 0. Since it is fixed, Q2 will also be 0. This is not fixed. Okay, so we have to find out Q3, we have to find out Q4. This is fixed. So Q5 and Q6 will be 0. And wherever you have 0, straight away write the reactions. F1 is R1, F2 is R2. F5 is R5, F6 is R6, because this is 0 in the Q1. And left out is F3 and F4. Is there any force in the x direction? No, there is no force given in the x direction. So it is 0. Is there any force in the y direction? In the y direction? Yes, there is a force in the y direction, that is in the positive y direction of 100 kilonewton. So F4, in the negative y direction, there is a force of 100 kilonewton. So F4 will be minus 100 into 10 power 3 Newton is the force applied in the negative y axis. Okay. So next, once it is done, write the element connectivity table. So here element connectivity table has to be written in the trusses. So element 1, 2, write the initial node, final node. What is the initial node for the first element? Initial node for the please number the elements 1 and 2. This is the first element, this is the second element. So initial node for the first element is 1, final node is 2. Similarly for the element 2, initial node is 2, final node is 3. So 1, 2, 2, 3. Next x1, y1, x2, y2. You have to write this. Next LE, L and M you have to find out. So how do you write this x1, y1? Straight away write the coordinates of the first node. First node, what is the coordinate of the first node? 0, 0. So 0, 0. What is the coordinate of the second node? 1, 1. Okay, 1, 1. So straight away write 1, 1. Similarly, coordinate of the second node is 1, 1. Coordinate of the third node is 0, 1. Just write its respective coordinates. Don't break your head there. Next, find out LE, L and M for each of this thing. Okay, for the first element, what is LE? We have the formula LE is equals to, from the derivation, I have derived this already. LE is equals to root of x2 minus x1 whole square plus y2 minus y1 whole square. So for element 1, find out LE. x2 minus x1 whole square plus y2 minus y1 whole square, you will get LE is equals to root 2. Similarly, L and M. L is equals to x2 minus x1 divided by LE. M is equals to y2 minus y1 divided by LE. We have seen this, how we got this in the derivation, correct? So just write x2 minus x1 divided by LE. LE is this one. So you will get 1 by root 2. Similarly, y2 minus y1 divided by LE, you will get 1 by root 2. LE, L and M is you have got for the first one. Similarly, find out for the second element, LE, L and M. LE, what is the formula? Same. LE is equals to x2 minus x1 whole square plus y2 minus y1 whole square. LE, you've got it as 1. Similarly, find out L and M. L is equals to x2 minus x1 divided by LE. M is equals to y2 minus y1 divided by LE. So 0 minus 1 divided by 1, 1 minus 1 divided by 1. So you will get minus 1 and 0 as the answer. Okay. So just find out that. Once it is done, write the element stiffness matrix for a truss element. What is the element stiffness matrix for a truss element? K is equals to AE by LE, L square LM minus L square LM. We have derived this just now. Okay. Similarly, write this for element 1 and 2. So for element 1, K1 is equals to substitute A1 E1 divided by L1. Okay. Or LE is for the first element. You have to substitute for the first element. So substitute this L square LM minus L square LM for the L square LM minus L square and LM of the first element only. Okay. So this is for the first element. Just substitute it and then simplify it. Write its coordinates 1, 2, 3, 4, 1, 2, 3, 4. That is Q1, Q2, Q3, Q4, Q1, Q2, Q3, Q4. Okay. Next, go for K2. AE divided by LE. This LE is the second element 1. You can see here, this will be the second element 1. Even L, M, LM and LE, L square will all be, when you're writing for K2, will all be the second element 1. So write all the second element 1. Just take 10 power 3 as common, simplify it. Next, this one, number it. Second element is between the nodes 2 and 3. Node 2 has Q3, Q4. Node 3 has Q5, Q6. So 3, 4, 5, 6, 3, 4, 5, 6. Next, add this K1 and K2. Add K1 and K2. That is the global stiffness matrix. K is equals to 10 power 9. 10 power. Okay, you can take 10 power 3 or 10 power 9 as common. I'm taking 10 power 9 as common. Next, add this and that. Okay. Write Q1, Q2, Q3, Q4, Q5, Q6. Q1, Q2, Q3, Q4, Q5, Q6. Because it is still Q6. Correct? Element is still Q6. It is still Q6. So it is 6 cross 6 matrix. Now carefully write the first matrix. it is still 1 2 3 1 2 3 4. Write the first matrix, this one. Next write the second matrix, it is 3 4 5 6 3 4 5 6. Okay, so this part is added, this part is added here. Write all the other things as 0. Okay, next the similar step like we have solved in the bar. KQ is equals to F, we have the K, Q is equals to F. F we know, R1 R2 0. Where did we get this from? We have got this from here. R1 R2 0 minus 100 into 10 power 3 Newton, 0 sorry R5 and R6. Next, using elimination method, strike off the rows and column wherever we have 0. Okay, so here we have 0, first row first column 0, second row second column 0 in the fifth row fifth column, 0 in the sixth row sixth column. Okay, just strike off that. Next, multiply 10 power 9 common, this into this, that is 2.85 into Q3 plus 0.75 into Q4 is equals to 0. 0.10 power 9 common, 0.75 into Q3 plus 0.75 into Q4 is equals to minus 100 into 10 power 3. If you simplify this to find the unknowns, two equations, two unknowns, if you solve it simultaneously or in your calci, you will get Q3 is equals to 4.761 at 10 power minus 5 meter, Q4 is equals to minus 1.827 at 10 power minus 4 meter. Okay, next to find the reactions similar to the bars. R1 is equals to 0.75 into 0, 0.75 into 0, minus 0.75 into Q3, minus 0.75 into Q4, 0, 0. 10 power 9 common. Similar equation. You will get R1 as 99966.6 Newton. Similarly, R2 minus 0.75 into Q3 minus 0.74 into Q4. Okay, simplify this and this, you will get R2. R5 this and this, R6 this and this, you will get R6. R2, R5 and R6, we are getting it as 0. Okay, so like that, find out all the reaction forces. Now we will find the stresses. Sigma 1 is equals to E by LE. Sigma 1 is equals to E by LE minus L minus M, LM, Q1, Q2, Q3, Q4 is the formula we have. It's all epsilon is equals to 1 by LE, right? So, Young's modulus is equals to stress by strain. So we have got this equation. So sigma 1 is equals to E by LE minus LM, LM, Q1, Q2, Q3, Q4. Just substitute the values of the L and M of the first element, that is when you are doing for the sigma 1. Multiply this row and this column. Okay, you will get this. Multiply this with this, you will get sigma 1. Similarly, sigma 2, E by LE of the second one, that is second element. Then minus L minus M, LM of the second element. Next, Q3, Q4, Q5, Q6. Okay, for the first element it is Q1, Q2, Q3, Q4. So the second element it is Q3, Q4, Q5, Q6. Correct. Second element is between Q3, Q4, Q5 and Q6. Okay. So just multiply this and this, and multiply this and this, simplify. You will get sigma 2 is equals to 999,8100 Newton per meter square. Okay. So here we have substituted everything in meter square. So we have got in meter square. Okay. So keeping this as a reference, quickly we will move on to the next problem. All the problems are very similar in the truss. Only if you know the first step properly, rest everything is similar. Okay. So second problem is almost the same thing, but it is given in mm. This is 500, this is 750. 50 kilonewton in the negative y-axis. Area of the first element is 1000 mm square. Area of the second element is 1200 mm square. E is 200 GPa. At the free body diagram, this is fixed, this is fixed. Write the nodes 1, 2, 3, element 1 and element 2. Write the coordinates, left bottom corner as origin, this will be the origin, so 1 is 0, 0, 2 is in the x direction it is 750, in the y direction it is 500, 750, 500. 3 is 0 and 500, 0, 500, x is 0 and y is 500. Now write the displacement and the forces q1, q2, q3, q4, q5, q6. Okay, forces f1, f2, f3, f4, f5 and f6. This is fixed, so q1 is 0, q2 is 0, this is fixed, so q5 is 0, q6 is 0. Wherever you have 0, write the reactions r1, r2, r5, r6 straight away. Now f3, is there any force given in the x direction? No, so it is 0. f4, is there any force given? Yes, minus 50 into 10 power 3 Newton. Next write the element connectivity table, element 1, 2, initial node, final node. So first element is between the nodes 1 and 2, 1 and 2. Second element is between the nodes 2 and 3, 2 and 3. x1, y1, x2, y2, LE, L, M, LM. So first node between the coordinates 1, 0, 0. Second node the coordinates is 750, 500. Second node coordinate 750, 500. Third node coordinate 0, 500. So 0, 500. Now find out LE, L, M and LM using the formula. LE is equals to root of x2 minus x1 whole square plus y2 minus y1 whole square. Find out this for the first element. Similarly find out this for the second element using the appropriate formula. Okay. Next you have the element stiffness matrix. K is equals to AE by LE. You have the finite element, element stiffness matrix of a truss element. Now find out for the first element. K1 is equals to area of the first element, that is A1 E divided by LE. LE you have to use for the first element when you are doing for the first, that is 901.8. Then L square LM, L square minus L square minus LM, same thing you have to use for the first element, L square M and LM. Okay, all this thing for the first one you have to use it. Take 10 power 5 as common, multiply everything to the inside. So this is between the nodes 1, 2, 3, 4, that is q1, q2, q3, q4, 1, 2, 3, 4. Okay, next for the element 2, k2 is equals to A2 E divided by L2. Sorry, A2 divided by LE. LE is 750 for the second element. You have to be very careful in this, and area of the second element is 1000. So even L square LM minus L and my LM also you have to use for the second, same which you have got for the second element. So similarly find out K2, 10 power 5 common, take everything inside. Write its global degrees of freedom, that is Q3, Q4, Q5, C6, 3, 4, 5, 6. Okay. The 6 cross 6 matrix will be the global stiffness matrix. Global stiffness matrix will be a 6 cross 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Write the first matrix, that is the K1 matrix. Here 1, 2, 3, 4. Sorry, it is still here. And write this one, which starts from 3 cross 3. This and this. So only this part will be added. Okay, this is a global stiffness matrix. Next, the finite element equation, KQ is equals to F. KQ is equals to F. Q you know, F you know. We've got from here Q and F we have already written here. Okay, so using the elimination method, eliminate the particular row and the particular column. Wherever we have 0, eliminate that row and that column. Here we have 0, eliminate first row, first column, 0, second row, second column, 0, fifth row, fifth column, 0, sixth row, and sixth column. So remaining is whatever we have added that part. So multiply this and this like the previous problem itself. You will get two equations. Solve for that. You will get Q3 and Q4. Similarly, reactions R1, R2, R5, R6. So this and this you will get R1 second row, and this column you will get R2 fifth row, and this column you will get R5 sixth row, and this column you will get R6. Okay, R1, R2, R5, and R6 is 0. Okay, similar to the previous problem like we have solved. Then sigma 1 is equals to E divided by LE minus L minus M LM Q1 Q2 Q3 Q4. Simplify it, you will get 75.66 MPa. Sigma 2, same thing, E divided by LE of the second element minus L minus M LM of the second element and Q3 Q4 Q5 Q6 here. This is Q3 Q4 Q5 Q6. For the first element Q1 Q2 Q3 Q4. For the second element 3 4 5 6. Okay, next is sigma 2, you will get it as minus 75.2 MPa. See, for the first element Q1 Q2 Q3 Q4. For the second element Q3 Q4 Q5 Q6. Okay, that's how you substitute here. Alright, so next we'll move on to the next problem. Okay, so it's a it's in 3 element one. Okay, the length of height of this is 1.5 meter. At this point it is completely fixed. At this point we have it is supported on a roller support, and a force of 12 kilonewton is applied in the y direction, the negative y direction, and in the positive x direction force of 8 kilonewton is applied. E is given as 200 GPa, A is given as 800 mm square. This is 2 meter and this is 2 meter. So write this finite element model. We'll start numbering the nodes 1, 2, 3. Just move in one direction. Okay, 1, 2, 3. Start numbering the elements. Element 1, element 2, element 3. Just move in the one direction. Keep in mind we'll always move in the anti-clockwise direction. Next, always select left bottom corner as the origin. So if this is origin, 1 is 0, 0. 2 is 4 meter and x is 4 meter, y is 0. So 4000 mm and 0. Next, this is 2 and 1.5. So 2000 and 1500. Okay, in mm. Next, displacement and forces Q1, Q2, Q3, Q4, Q5, Q6. Forces F1, F2, F3, F4, F5 and F6. Since this is completely fixed, Q1 is 0, Q2 is 0. Okay, coming to this point, it is a roller support. It is a roller support, so it can move in the x direction. So Q3 will not be equals to 0. Q3 we have to find out, put it as a question mark. Q4, in the y direction it is fixed, roller will not move in the y direction, so Q4 is equals to 0. Next, Q5, there is no fixed condition here, so Q5 we have to find out, and Q6 also we have to find out. Okay, next forces, F1, it is completely fixed, so there will be reaction in the x direction and reaction in the y direction, so R1 and R2. Here it is free in the x direction, so F3 is equals to 0, there won't be any reaction. But it is fixed in the y direction, so F4 is equals to R4. There will be some reaction since it is fixed. Okay. And coming to this point, F5, there is a force given in the x direction, in the positive x direction, that is 8 into 10 power 3 Newton. Similarly, force given in the y direction, that is F6, that is minus 12 into 10 power 3 Newton, that is in the negative y direction. Okay. So this is just coordinates positive, positive, negative, negative for your understanding. Rest all the steps is similar if you do till this one. Next, element connected table E 1, 2, 3. Initial node, final node. First element is between the nodes 1 and 2. 1 and 2. Second element between the nodes 2 and 3. Third element is between the nodes 3 and 1. Okay. So first element coordinate 0, 0. First node coordinate 0, 0. Second node coordinate 4000, 0. Second node coordinate 4000, 0. Third node coordinate 2000, 1500. Similarly, third node coordinate 2000, 1500. First node coordinate 0, 0. Now find out LE, L, M, L square, M square, or LM everywhere, everything in this table itself. Okay, and LM I found out here. Okay, and you can directly do this in your calci using the same formula. LE is equals to root of x2 minus x1 whole square plus y2 minus y1 whole square, and L is equals to x2 minus x1 divided by LE, and M is equals to y2 minus y1 divided by LE. Okay, you can do this for each and every element and you can find the values. Okay, once you do that, next is the K1. That is same. What is the formula? A by LE minus L square LM minus L square and LM. You have to remember this formula. Then substitute the particular values of the first element here and take 10 power 4 as common. And write the global degrees of freedom. 1, 2, 3, 4. Okay, this is K1. Similarly, do for K2, A by LE, same thing, 3, 4, 5, 6. This is K2. Similarly, write for K3, A by LE for the third element, L square LM minus LM minus LM and minus L square and minus LM. Just simplify this. And the third one, see, while writing the third one, what is the global degrees of freedom? See, here till here I wrote 3, 4, 5, 6. But third one is, I am writing it as 5, 6, 1, 2, 5, 6, 1, 2. What is the reason for that? See, the